Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, water, steam, and ice. Water is probably the most important chemical in our everyday experience. We're largely water ourselves and water is all around us. And it takes three familiar forms, water does. One of them is ice, the solid. One of them is water, the liquid. And the third is water, the gas, which we can call either steam or water vapor. And these three forms of water are very important in everyday experience. So we're going to spend some time looking at the three phases and how they convert from one to the other. So first, what is water, ice the solid as opposed to water the liquid as opposed to steam the gas? Well, ice the solid consists of water molecules, as all three of these things do, but the water molecules in ice are arranged in a crystalline lattice, which is to say they are organized in a repetitive, consistent, orderly structure. There is some interesting disorder to an ice crystal, but for all practical purposes, it's a lattice work, and by that I mean it's kind of like the array of oranges at an elegant grocery store where they have stacked all the oranges in lines and rows of rows, and it's all neatly assembled there. And knowing where one orange is or two oranges is tells you a lot about where all the other oranges are, because they're predictably along lines and other geometric patterns. So that's ice. Ice, the water molecules are arranged in this orderly fashion. Furthermore, they are touching each other as best they can, but they are not able to move relative to one another. So if you know where one water molecule is, it's pretty much going to stay there indefinitely, and then next to it's the same neighbor, the same other neighbor, and so on. It's all, the lattice work is pretty static. Compare that with liquid water. In liquid water, the lattice work is all messed up. It's not such an orderly array of water molecules. They are still touching each other, but they're moving about and they're changing partners periodically, so that the water molecules that were sitting together at one moment will soon become separated. You can't really predict that they're going to stay together for any length of time. And that mobility of the water molecules allows the water to flow. Now it's not a solid anymore, it's a liquid. It's got a fixed volume for all practical purposes because the water molecules still touch each other and they kind of fill the environment with water molecules is sort of almost as tightly packed as possible, but they can move about, so the liquid water can change shape. What's the last possibility? Water the gas, which you can call your steam or water vapor. In that case, the water molecules have let go of each other. They're now independent agents. They're traveling around with thermal energy, and they bump into each other and collide and may cling briefly, but for all practical purposes, again, I guess I'm using that phrase a lot today, they're just on their own. Off they go and bounce around. They're a gas. Well, to go from one of these forms to the next involves energy. So if you start with water as ice, solid ice, the water molecules are effectively bound to each other, not with formal chemical bonds, not really the strong chemical bonds, for example, that hold together the molecules of life, so-called organic molecules, which cling to each other in which the atoms cling to each other with what are known as covalent bonds. In water, the separate water molecules cling to each other quite strongly with bonds that are close to full chemical bonds, or arguably could be true chemical bonds. They're known as hydrogen bonds, but they're gripping each other, but you can get them apart more easily, in fact, than you can get apart the organic molecules of life. So in ice, the water molecules are gripping each other pretty well. If you want to free them up so they can become liquid water, the water molecules now have some mobility, you have to invest energy into the material. There is what's known as a latent heat, which is to say a latent amount of energy in the form of heat typically, that frees up the water molecules from being water in ice to water in liquid water. So you have to invest energy to convert ice into liquid water. Similarly, if you go the other way, if you take liquid water and you want to get the water molecules to cling to each other tightly enough to become a lattice work again and become solid ice, you have to remove energy. So they develop the energy debt that is associated with chemical bonds, in this case the hydrogen bonds, the ones that cling the water molecule together. So you have to invest the latent heat of melting, or more formally, it's often known as latent heat of fusion. The latent heat of melting is the energy you have to invest in solid ice to melt it to make liquid water. And you're freeing the molecules up when you do that. The latent heat of melting is measured in energy per unit of material. And the unit of material would be a kilogram, the SI unit, 1 unit of mass of the material. So to melt one unit of 1 kilogram of water takes a certain amount of thermal energy to melt it. All right, let me go on to the next possible transition, which is liquid water to gaseous water. To convert liquid water into gaseous water, you actually have to pluck apart the water molecules completely, so they're no longer clinging to each other, even as they were in liquid water. And that takes quite a lot of energy, because now you're really breaking all those so-called hydrogen bonds, pulling apart. So there is, again, a latent heat, an energy that you have to put in to turn liquid water into gaseous water. And it's it's one of the biggest latent heats of what is called latent heat of evaporation or of vaporization, just two different names for the same thing, of any material. It takes a surprisingly large amount of thermal energy to turn liquid water into gaseous water. And I should say that in both of these stories where I've taken you from solid to liquid and from liquid to gas, both of which require the investment of a latent heat. That is, you have to add energy to convert solid ice into liquid water. You have to add energy to convert liquid water into gaseous water. Behind that is another observation, that we're doing this without changing the temperature. So even if you don't change the temperature, you go from ice at one temperature to liquid water at the same temperature. So you're not heating things up. It still takes energy. How much energy? The latent heat of melting. And when you go from liquid water to gaseous water without changing the temperature, just freeing up the molecules, you have to put in a latent heat, the latent heat of evaporation or of vaporization. And both of those latent heats are big for water, all right? So I'll come back to that later on, but the point is I'm trying to set the stage for the three phases of water: solid ice, liquid water, gaseous, steam. And that there's an energy barrier to going from one to the other. You want to convert solid ice into liquid water, you got to invest some energy. You got to free up the molecules so they can move relative to one another. You want to turn liquid water into gaseous steam, you got to invest some energy. You got to free up the water molecules so they're independent of each other. All right, let's go back now to solid ice and liquid water. Let's see, can you have both of them, for example, at the same time? Or when is one around and not the other, or vice versa? At very low temperatures, you're pretty much going to only have solid ice. If you take away enough thermal energy from the system, the water molecules will cling to each other as tightly as they can. You will enforce the minimum of available energy so that they're going to grab onto each other tightly. They're going to arrange themselves in a lattice. You're going to have solid ice everywhere. At much higher temperature, there's a lot of thermal energy around. The ice, it turns out, is going to become unstable, and you're going to have liquid water around a lot, maybe even entirely. So what are the rules governing when you have one versus the other, and can they ever coexist? Well, let's actually look at the moment of coexisting. They can coexist. They coexist at a very familiar temperature, which is the melting temperature of ice or the freezing temperature of water. I hope you know it. For people in the United States, it's often known as 32 degrees Fahrenheit. Using a temperature scale that's sort of unique to the Americas, or to the United States. In degrees Celsius, it's basically 0 Celsius. So at that special temperature, water and ice, so solid and liquid, can coexist. And what's going on there? Well, if you look at the surface of the ice, or equivalently the surface of the liquid water touching the ice, those two surfaces, they're exchanging water molecules, which is to say that water molecules are periodically breaking free of the crystalline lattice that is solid ice and becoming part of the liquid water. And at the same time, some water molecules are breaking free of the liquid water and sticking onto the solid ice and becoming part of its lattice. So there's an exchange of water molecules. And if the exchange is occurring such that it's at the same rate, water molecules are leaving the ice for the water, as often as they are leaving the water for the ice, you have what's known as phase equilibrium. The two phases aren't growing or shrinking. They are exchanging molecules, but they're making no progress from one form to the other. And that can occur if you actually have this balance. You have to have water molecules leaving the liquid at just the right rate to go on the solid, and they have to leave the solid just right to go on liquid. If you hit balance, poof, the ice and water will coexist and stay that way forever, indefinitely. What determines the rates in those two cases? Well, thermal energy is a big player in the story. If for a water molecule on the ice, in the ice lattice, to break free of its neighbors, free itself up so that it can become liquid water with its increased mobility, it needs energy, right? The latent heat of melting. So something's got to invest energy in it. And that energy can come from just the ambient thermal energy. Once in a while, the thermal energy, because it's distributed statistically, one water molecule will get more than its local fair share of energy just by random chance, and it will break free of the solid ice and become part of the liquid water. Hey, great, it's freed up. The higher the temperature, the more likely that event will be, and so the greater the rate at which water molecules will suddenly find themselves free of the lattice. Wow, we're suddenly free, we can move around like liquid. So with increasing temperature, you get faster leaving of solid ice, of water molecules from solid ice into liquid water. The returning rate of water molecules from liquid water onto solid ice is determined primarily by how often the water molecules sort of touch the ice. The liquid water molecules are rattling around, they touch the ice, they rattle around, they touch the ice, and periodically when they touch, they lose the thermal energy, that they release the latent heat of melting and stick. So something sucks away their energy and they get stuck on the surface of the ice. And that rate, that returning rate, the rate at which water molecules leave the liquid water for the solid ice, is determined largely by how dense the liquid water is, which is sort of, how often the molecules hit the ice. Well, it's determined by how packed they are. That's not going to change very much. So that's relatively temperature independent. The returning rate doesn't depend a lot on temperature, but the rate at which water molecules break free of the ice definitely does depend on temperature. So you would expect then that at very low temperature, the water molecules are not going to leave the ice very often. They can't get the energy. The landing rate is going to still be there. And so at very low temperatures, liquid water is going to land more molecules on the ice, which grows, than leave the ice for the liquid water, and the ice is going to get bigger and bigger. The liquid water is going to gradually disappear. So at low temperature, ice becomes the only stable phase. Liquid water just shrinks away to nothing because its water molecules just land on the ice and stick too often and don't get replaced. Go to the other extreme, relatively high temperatures, where water molecules easily find enough energy to break free of the ice. The ice keeps tossing off water molecules into the liquid water, and they return, but at the usual rate, which isn't fast enough. So the solid ice melts. It just disappears gradually because its water molecules break free too often, and they leave. In between these two extremes, there will be a point at which the balance occurs. And at that balance point, the water and ice coexist in phase equilibrium. Neither phase grows at the expense of the other. And that occurs at a specific temperature, and it is 32 Fahrenheit or 0 Celsius. That's the way it turns out. And That's why there's a special temperature at which the two phases coexist. You go below that temperature, the ice shrinks. It loses molecules too fast. You go above that temperature, you go below that temperature, the ice grows. It gains molecules too fast, doesn't lose them fast enough. If you go above that melting temperature, the water molecules leave the ice too often and the ice shrinks away to nothing. I hope I've said that correctly now. Right at the melting temperature, you get balance. So it is possible for the two of them to coexist at one temperature. It is 32 degrees Fahrenheit, 0 Celsius. And that's the temperature you'll find in any glass of ice water. If you look at a glass of ice water, it's been there for long enough for it to sort of settle down and get any extreme temperature imbalances out of the way. So it's all at one temperature. If it's got ice in it and water in it, the two phases simultaneously, the only temperature which that can occur is 0 Celsius, 32 Fahrenheit. The water molecules are then landing and leaving the ice at essentially equal rates, and it can coexist. If you add heat to ice at that temperature, if you add heat to ice that is simultaneously to ice water, that has ice, the solid, and water, the liquid, you'd think the heat would raise the temperature, but oddly it doesn't. The heat goes in, and what it does instead of raising the temperature is it drives the phase balance. It forces more water molecules to leave the solid ice for the liquid water than return, and it shrinks the ice and enlarges the liquid water, but it leaves the temperature virtually unchanged. So as long as you still have both liquid water and solid ice, adding heat doesn't increase temperature. It just shifts the balance, melts some of the ice. On the other hand, if you suck heat out of the system, you put your glass of ice water in the freezer, and heat begins to leave the glass. Well, the temperature of the liquid solid the mixture doesn't drop. Instead, as you take heat out of that mixture of ice water, the liquid water shrinks in favor of the solid ice. The ice grows. You're growing bigger crystals of ice. Temperature stays pretty much right there at the melting temperature of water. A melting temperature of ice, 32 Fahrenheit, 0 Celsius. So that's the story of melting and freezing. That at very low temperatures, all you have is ice. At very high temperatures, all you have is liquid water. Right around 32 Fahrenheit, 0 Celsius, it's possible to have both. If you're below that melting temperature, the liquid water will shrink to grow the ice, and if you're above that temperature, the ice will shrink to grow the water. And right at that temperature, you can have both of them, and they can sit there for a while. And if you add or subtract a little bit of heat, you can shift the balance of the two phases, but the temperature will pretty much sit there. And some of this is driven and enforced by the latent heat of melting. The notion that to turn solid ice into liquid water, you have to invest energy to free up the water molecules. To turn liquid water into solid ice, you have to take out energy to unfree up the molecules so they cling to each other. And so that's the story of melting and freezing. Let's go to the next balance between two phases. Liquid water and gaseous water, or steam or water vapor. In that case, those two also can coexist. And there's a lot more flexibility in that coexistence. At very low temperatures, if you've got liquid water at all, it's very hard to get gaseous water. So the story is that at low temperature, the water molecules have difficulty breaking free of each other at all to become a gas. So if there is gas present in the vicinity around the liquid water, it's a very thin gas that is very low density, almost no molecules in it. Because if you look at the surface of the liquid water and the surface of the gas, they are exchanging water molecules, but it's very rare that a water molecule in the liquid water will find enough energy to break free. So it's not leaving very often to go into the gas. Whereas the molecules in the gas are just bouncing around, they're normal gas molecules, and they hit the surface periodically. When they do, they often stick. So at low temperatures, the liquid water is very reluctant to give up water molecules to the gas. The landing rate will tend to dominate, and you'll tend to just get rid of the gas. The water molecules in the gas will just become rare. So you have mostly gaseous liquid water. At the highest temperatures, the water molecules can easily get enough temperature, enough thermal energy, more than their fair share, or even just their fair share, or maybe enough to break them free of their buddies and fly off as gas. So at high energies, it's easy for water molecules to leave the surface of liquid water, go off into the gas, and although they're still will be landing back on liquid water periodically, just as random gas molecules do, this at high temperatures it favors having an awful lot of them up there in the gas. They easily can break free and accumulate up there as gas molecules. So, to summarize this so far, at low temperatures, you can have both liquid water and gaseous water, but there will not be very many water molecules in the gaseous phase. It's going to be a very low density. At the higher temperatures, the highest temperatures, you can have both liquid water and gaseous water. But most of the water molecules are going to be in the gas phase because it's so easy for them to get up there. They can easily find the energy they need to break free and rattle around up there as gas. So you can have phase coexistence, liquid water and gaseous water. You can have the two of them sitting there together, not growing at the expense of one another, over quite a range of temperatures. What will be different between the two, however, is the density of the gas. At low temperatures, they coexist when the gas is a very dilute, very low density gas. At high temperatures, the two coexist when the gas up there is dense, packed, heavy duty steam. All right, so how about converting one to the other? Well, to actually convert liquid water to gaseous steam, you have to invest the latent heat of evaporation or vaporization. So it takes some heat flow to convert one to the other. So if you raise the temperature, suppose you have these two in phase equilibrium at low temperature, and you decide to heat it up and try to shift it to a new phase equilibrium at higher temperature. That's going to involve evaporating a word I didn't mean to use exactly yet. That means you're going to convert a lot of liquid water into gaseous water. That's going to require investing a lot of thermal energy. So you will add thermal energy both to shift the temperature up towards higher temperature, and you will also have to add thermal energy, heat, to change the phase balance from a lot of liquid water and almost no gas at low temperature to less liquid and a lot of gas at high temperature. So the energy going in, shifting the balance, you have to pour in a lot of heat to raise the temperature of this mixture of liquid water and gaseous water. I did bring up the word evaporation. Evaporation is a phase transition from liquid water to gaseous water. So if there's a net movement of water from the liquid phase to the gaseous phase, it is said that the water is evaporating. And that will happen as you take this balanced system and heat it up thermally. You raise its temperature by adding in thermal energy, adding in heat. You can shift the balance so you got more and more steam, less and less liquid water. That's evaporation. If you do the reverse, you start with a balance between at high temperature, liquid water and gaseous steam, and there's a lot of water molecules in the gaseous phase at high temperature. So you cool it down. Now the gaseous phase shrinks. It loses molecules to the liquid phase. Liquid phase grows, more molecules in it. That's called condensation. So you can anytime you shrink the liquid phase for the gaseous phase, that's evaporation. Anytime you shrink the gaseous phase for the liquid phase, that's condensation. They both involve the latent heat of evaporation or vaporization. Evaporating the water, when you make more gas molecules, you got to pay the piper. You have to invest the energy, the latent heat of evaporation necessary to break the water molecules free of each other and send them off as gas. When you condense the water vapor or the steam, now you have to have the water molecules stick together, cling together as a liquid. You have to take out the latent heat of evaporation or vaporization to allow them to stick. So they release that latent heat. So that's evaporation and condensation. I should point out the concept of relative humidity at this point. I've been describing this and waving my hands saying that everything's in phase equilibrium whenever possible, so that you sit at one temperature with both liquid water and gaseous water, and there's no net movement of molecules from one to the other. Same at high temperatures. It's just for me, a simple environment to think about it. But now, you're not always in situations that are at phase equilibrium. For example, if I took a glass of water and just set it here in the middle of the table, we would not be at phase equilibrium, even if the whole temperature of the room was uniform. So suppose it's it's room temperature, which is approximately 20 Celsius or 70-ish Fahrenheit, and I set a glass of water down there. If we came back tomorrow, the glass would be pretty much empty. The water would have evaporated. Well, why? Nothing changed temperature and all that. Where did the water go? Well, it's because in this, where we are right now, where I am right now, there is liquid water in the glass, but there would not be enough water molecules in the gas phase, as we started out, to reach phase equilibrium. The water molecules would leave that liquid water for the gas, which includes air molecules that have very little role in the story. Basically, there's some water molecules here between my hands in the form of gas, water vapor. They're there, but they are not dense enough to balance liquid water at room temperature. So if you look at the landing and leaving process, the leaving the liquid water for the gas and the landing from the gas to the liquid water, the landing isn't fast enough. There are just not enough water molecules here to replace the ones that leave the liquid water. Liquid water is going to shrink. We're going to get more water molecules in the gas phase. The way of describing this situation, where the air here doesn't have enough water molecules in it to balance the leaving of water molecules from liquid water at this temperature, is we describe this in terms of relative humidity. Suppose there were enough water molecules up here to balance, so that the landing and leaving were perfectly matched. The liquid water would just sit there all day. It would secretly be exchanging water molecules with the air, but you wouldn't see any effect. The water would be there today, tomorrow, the next day, same water. It looks like the same water. It hasn't shrunk, no change. If that were the case, we would say the air is at 100% relative humidity. There is enough water vapor in the gas phase of this air to balance the phase of liquid water. So they exchange there's no net exchange of water molecules. In principle, if the relative humidity were greater than 100%, the water molecules would be so dense up here that they would land too often and the water would grow. We get condensation. But more likely is the situation I described in setting up this story, and that is that there are not enough water molecules up here to replace the ones that leave the liquid water. In that case, the liquid water gradually disappears, and water molecules enter the gas phase more often than they leave the gas phase. In that case, the relative humidity is less than 100%. For example, it might be 50%, meaning there are only half as many water molecules per volume up here as is required to achieve balance. In that case, water molecules will leave the water too often, more often than they land. The water will gradually disappear. The water phase will gradually disappear. The gaseous phase will gradually get a little more dense, more water molecules in it. So relative humidity is telling you which way water is going to move. If the relative humidity is 100%, there will be no net movement between the gas and the air, that is, the air and liquid water that happens to be sitting in a glass or somewhere else. If the relative humidity is above 100%, you're going to get a net movement of water molecules from the gas to the liquid water. If the relative humidity is below 100%, you're going to get a net movement of water molecules from the liquid water to the gaseous water. And when the relative humidity gets quite small, for example, 10%, like you might get it in a desert, the rate is almost, the water molecules are leaving almost as fast as they can because there's almost no return at low relative humidities. All right, so that's the story of evaporation, condensation, relative humidity. There are since we've got 3 different phases to work with, solid, liquid, gas, there are 6 ways the transitions can occur from solid to liquid, liquid to solid, from liquid to gas, gas to liquid. It turns out there are 2 more left, from solid to gas and gas to solid. And those might seem like, who invented those? Where'd those come from? Well, they're there, and they're familiar even. It is quite possible for water molecules to break free of ice, not become liquid water, but rather become gaseous water. They break completely free, right out of the lattice, poof, and head off as gas. In doing that, they need a lot of energy because they need the energy both to break free of each other so they can move a little bit, and break completely free of each other so they can move as gas. They need both the latent heat of evaporation and the latent heat of melting and latent heat of evaporation. They need them both. But this can happen. Water molecules can break completely free of the solid ice and go off as gaseous water. That phenomenon where the water molecules skip the liquid phase and go right to the gas is called sublimation. And it's familiar, actually, to anyone who has a frost-free refrigerator, or often when you watch a period once you've got ice and snow outside and the temperature never gets above melting, so that the ice and snow just sit there for days on end. They shrink. And the same thing happens in the freezing compartment of a frost-free refrigerator. The ice cubes just shrink. Where's the water going? The water, the chemical going? It's leaving the ice for the gas phase directly, and it's skipping the liquid phase. It's subliming, or sublimation. Water sublimes right off of ice, and it causes the snow and ice around your house to just gradually diminish, get smaller and smaller as the days remain cold, but the water escapes. It finds the thermal energy it needs to just break free as gas and leave. Same thing in your freezer. It causes, not only does it cause the ice cubes to shrink in the ice trays, but it causes what's familiarly known as freezer burn of food. If you don't wrap food properly, the moisture just leaves. And so you end up with food that's kind of dehydrated and therefore not very pleasant. That's water subliming off the ice. It involves a lot of energy because the water molecules have to completely break free of the crystal and head off into gas. And it occurs when the relative humidity above the ice is less than 100%. Relative humidity actually applies to the situation of ice and solid ice and gaseous water. At low temperatures, there's no liquid water around. There's just the ice and the gas, and they exchange molecules, and at 100% relative humidity, they're exchanging it in perfect balance. At less than 100% relative humidity, the ice is shrinking and the gas is growing. At above 100% relative humidity, the gas shrinks and the ice grows. And that's a process called deposition, and it's familiar too as frost. So on certain circumstances when it's cold outside and the air is humid, the water can just land right out of the gas phase onto surfaces and grow ice crystals. And they'll grow on windows, they'll grow on the grass. And we call it, the familiar name for that is frost, and the highfalutin name for that is deposition. When that happens, it releases a lot of energy because the water molecules are going from the gas phase to the full crystal and sticking together of a solid ice, and that releases the latent heat of evaporation and the latent heat of melting, both at once. So lots of energy comes out during the process of deposition. All right, so that's the 6 possible phase transitions between ice to solid, water to liquid, and steam to gas. What about boiling? Where does boiling fit into this? Well, it turns out boiling is not a new phase transition. It's just evaporation on steroids. It's a very rapid form of evaporation. And what makes it rapid? Well, in normal evaporation, when you just got say a pot of water, maybe it's on the stove, maybe not, pot of water, it's only got the top surface exposed to the air and therefore the gas phase. So water molecules are exchanged between the liquid water and the potentially gaseous water only through that top surface of the water, a surface area about this big. Not very much. So it may take a long time. Even if the air is has very low relative humidity, so meaning there's just not much water vapor up here. So every water molecule that leaves, the liquid water is not replaced. So in that case, the water will gradually shrink, but it might still take a couple days at ordinary temperatures for the water to shrink enough that you notice it. If you go hotter, the water leaves more often because the water molecules find the energy they need to break free more often, and they leave more often. But still, you're only getting evaporation through that top surface. What about if you could froth up the water so it had more surface? There are more places in which the water had the opportunity to leave the liquid to become a gas. Well, for that to happen, you have to open up empty spots inside the water, and empty spots don't survive very long in this environment where the atmospheric pressure tends to crush stuff. You can't blow up a balloon full of nothing. It gets smushed by the surrounding air. So you got to fill it with something. Well, you could fill it with air, but who's going to be there blowing bubbles in the water to sort of make extra space? If you do that, if you blow bubbles through water, you will speed up evaporation, assuming you use low humidity air to do that. But there's another possibility. You could actually make a bubble that's full of water vapor. So it's got water vapor inside it, no air, just water vapor, and now more water molecules can leave and enter it and join them, and join the water molecules that are already there as gas, so the bubble can grow and get bigger and bigger. For that idea, it's a good idea, and actually it's going to be behind boiling, but for that to work, the water vapor has to have enough pressure in it to keep the bubble from being smashed by atmospheric pressure. So you need the water vapor to be pretty dense. And what temperature, at what temperature does the water vapor become dense enough to tolerate the crush of atmospheric pressure around? Well, that temperature happens to be here near sea level. It happens to be about 212 degrees Fahrenheit or 100 degrees Celsius, the familiar boiling temperature of water. At that temperature or above, steam can exist inside a bubble and be dense enough to have atmospheric pressure or greater. And therefore, the surrounding atmospheric pressure can't smush the bubble. So you can have stable steam bubbles for the first time at that temperature or above. All right, in that case, if you have one of those bubbles, a steam bubble in the middle of the pot of water, it can grow by evaporation. It's got new surface available through which the water molecules can break free of liquid water and become gaseous water and make the bubble bigger and bigger and bigger. And instead of having only this much surface area available to it, the water now in the pot has this much plus the surface area of its first bubble, and maybe its second bubble, maybe its third bubble, and lots of bubbles. The surface area available for evaporation suddenly becomes potentially very big. And that's what happens with boiling. When water boils, steam bubbles within the water are suddenly able to survive and grow by evaporation. And so you get evaporation not just from the top surface of the water, but from the body of the water where all these bubbles are. And evaporation goes from being a relatively slow process to a dramatically rapid process. And things that happen at this point are, it gets very hard to raise the temperature of the water any higher, because as you put more and more thermal energy into the water to try to drive up its temperature, that energy gets sidetracked and used to pay the latent heat of evaporation to evaporate more water. So as you heat up a pot of water, when you hit the boiling temperature, 100 degrees Celsius, 212 Fahrenheit, you keep heating, the water doesn't get hotter anymore. For all practical purposes, it doesn't get any hotter. Instead, the heat you're pouring in goes into turning liquid water into gaseous water through all these bubbles. And so you get a kind of fixed temperature. And that fixed temperature is very useful. It means that if you put food in this environment, you know what the temperature of the food is being cooked in is. It's about 100 Celsius. So you put an egg in there, you know what people know from experience. You put an egg in 100 degrees Celsius water, it cooks to the extent you like it in a certain number of minutes. If the temperature were different, the egg would cook differently, but you've got a controlled temperature. That makes things very convenient. Well, if the air pressure in your world, your environment, isn't the usual atmospheric pressure, the atmospheric pressure at sea level, then things are a little different. For example, you go up into the mountains, the air pressure is less. A steam bubble has an easier time surviving the crush of atmospheric pressure because there isn't as much atmospheric pressure. So steam bubbles can exist and grow at lower temperatures. So at a mile high, you go to Denver, you go higher than that, you go up into the Andes Mountains or something like that, the air pressure is low. And therefore, water can boil at lower temperatures, maybe 95 degrees Celsius or 90 Celsius. In which case, if you use this for cooking, you're going to have to pay attention because you put an egg in 90 degrees Celsius boiling water up there in the high mountains, it's not going to cook as fast. So you have to correct for this. You have to recognize that water boils more easily at high altitude, and therefore it boils at a lower temperature. So don't count on the temperature being as high as usual. Last thing about boiling, that is, up to this point I've just sort of said, well, you've got a steam bubble in water. If you're above the boiling temperature, the right temperature, the steam bubble is stable against the crush of atmospheric pressure, things are great, you get boiling. But that assumed the steam bubble. It assumed the steam bubble that there was a steam bubble. What if there's no steam bubble? Well, then you can't have the steam bubble grow because there's no steam bubble to grow. All right? What starts the steam bubbles? And that turns out to be an interesting question. In most situations where you're pot of water on the stove, for example, the pot starts the bubbles. The pot has hot spots, it has defects on its surface, it has little empty spots, little caves that trap air. Junk triggers the bubbles, nucleates the bubbles. It provides the initial seed that becomes the bubble. And you don't pay much attention to this until you sort of look into the pots. Do this, look into the pots and realize, all the bubbles are coming from the same spot, what I sort of think of as bubble nurseries, little places where the bubbles are first originate. And it is possible to create situations where there are no bubble nurseries, nothing to nucleate the bubbles, in which case you don't get boiling. And that's dangerous. If you heat water up in a situation in which nothing triggers the boiling, you can get the water much hotter than boiling temperature. Because when you add heat to water that's just evaporating off its top surface, some of the heat goes into evaporating water, but a lot of the heat goes into raising the water's temperature. So the water's temperature rises, its evaporation rate increases, and the two keep going. They go right through boiling and nothing special happens if there's nothing to create the first bubbles. And so you can go right past 100 degrees Celsius, 110 Celsius, 120 Celsius. And now you've got dangerous water, because if something does trigger boiling in the water, creates that first bubble, you can actually get basically an explosion where the first bubble grows so fast it shocks the rest of the liquid and triggers the formation of more bubbles, which trigger more bubbles. The whole thing just turns to steam very abruptly. And I turn out to be very good at doing this. There is a particular context in which you can superheat water, that is, take it past its own boiling temperature. That's known as superheating. And the context in which you can do this is microwave heating of water in a glass or glazed container. Glass or a glazed ceramic basically means it's got glass as its surface. So that glass surface is so smooth microscopically, right down to the atomic level, that it has no bubble nurseries, or if it does, it has only a few. And it is possible to take the water right through boiling and not have any bubbles form, in which case the water becomes dangerous and you don't want to do it. So when you heat water in a microwave oven and you know it should have boiled but it doesn't appear to be boiling, be a little careful with it, because you can have it can be above boiling temperature, and when you poke at it or shake it or stuff, you can trigger the boiling suddenly and it will just go kablooey as the whole thing boils very abruptly. So for safety's sake, superheated water is not a great thing. All right, well, that's the story of water, steam, and ice, the three phases of water, their conversions from one to another, transformations, phase transformations from one to another, the latent heats involved in going from one to the other. And with that, I will stop the story.